All right, welcome everybody. Hello. We are here for another Rust stream on the Microsoft Developer Twitch channel. I'm very excited to be here. Um, Yesterday I was on the stream. We talked a little bit about Rust, and then later on in the day, some colleagues of mine were on to talk more about Rust, specifically what it's good for, what you might use it for, various things about how to learn Rust and things like that. And today, what we're going to be doing is tackling the question of the borrow checker. And the borrow checker is, in some ways, the thing that makes Rust really special. And so we are going to be looking at that, examining it. We have about an hour, maybe a little bit more, this evening, this morning, this afternoon, wherever you happen to be. To look at the borrow checker and really to explore it and to get a better understanding. Now, after an hour, we probably won't have a deep understanding of what the borrow checker is all about, but hopefully, if you've done any Rust programming before, this will be a good way to kind of ask the questions that you might be struggling with to get a better feel of what's going on. With that being said, I'm going to switch on over here to this view here. And just a reminder that we are talking about Rust, of course. So if you want to learn more about the language, you can find the main page right here where you can find a lot of different information about Rust, including, very importantly, if you've not done so, rustup.rs, which is a tool for installing the Rust toolchain and core tooling that goes with it. So if you've not done so, make sure to go ahead and visit rustup.rs here. And if you're looking for the recommended way for writing Rust, I personally would recommend VS Code along with the Rust Analyzer extension, which is a really great extension and will soon, I believe, be the official extension for Rust. So check that out, and if you have any questions about that, let me know. Chat, I would really love to know what experience you have with Rust and how much Rust you've done before, whether that's absolutely zero all the way up to you've been writing it since 0.1 and you're in the inventor of the language. Would really like to know what experience you do have with the language, so that we can get a good feel of who we have here in the stream. As well as what type of different questions you might have when it comes to the borrow checker. All right, so I'm going to switch over to a terminal here. I'm running WSL on Windows here. This should work exactly the same way on Windows proper, on Linux proper, on Mac. Pretty much any operating system that you will be using, this should be exactly the same, so there's no real differences there. And what we're actually going to be doing today to kind of prompt our learning of the borrow checker is an exercise that is at first seemingly easier and more simple than what we did yesterday, which was writing a command line utility key value store database. Today, all we're going to be really doing is looking at some very short, very simple code snippets that in other languages would be kind of trivial code, but in Rust present us a little bit of an issue because we run up against the borrow checker, and for good reason. One of my goals for today is to convince you that the borrow checker is not there to make your life miserable, but is actually providing some real utility. So we'll look at what kind of bugs actually the borrow checker is saving us from. All right, so let's get started. As always, when you're writing Rust code, you usually start by creating a new cargo project. And again, cargo is Rust dependency manager, build tool, all wrapped in one. And you do that by saying cargo new, and we're going to say cargo new borrow, just as the name. All right, and that creates a new executable application for us. And as we saw yesterday, there's not too much to it. So I'm just going to open this up in VS Code right here. Oh, and way too big. All right. And let me go ahead, and resize this so everybody can see it well. And open up our main .rs here, where we have our main file here. So again, we can go ahead and just run that real quick just to prove to ourselves that it's working. Cool. So we have hello world being printed out to standard out here. And this is just what Cargo kind of creates for us by default when we create a new project. And we're gonna fill it in with different things. So what are we actually going to be building today? Well, I want to start out by modeling a group of people. And so I think the best way to do that in Rust is by having a struct called person. And let's say what the information that we want to keep about this person or these people is their age. And the age, let's say, most people are between 0 and 100, 120 at the very, very highest end. And so I think a U8, an unsigned 8-bit integer, is perfect for modeling that. And let's do height here, and I'm just going to do, let's say, height in centimeters. And I don't know, U8 is maybe a little bit too small for that, but we'll do it anyway. So all the way up to 255 centimeters, which is, if you're taller than that, you're quite tall. And I'm almost 2 meters tall, so I know that that's quite tall. All right. So I have a struct here, and a struct is, unlike a class in other languages, a struct is really just kind of data bundled together, just two unsigned 8-bit integers in this case. All right. And so let's say in our main function, instead of printing hello world here, we're going to create a collection of persons, collection of people. And so we call that people here. And, collections in Rust typically end up being vectors. And vectors are growable linear collections of things. You might know them by the name array in other languages. Arrays in Rust are fixed-sized things. Vectors are growable. So if we know exactly we need just 5 people and we'll only have 5 people, no more, no less, then we can use array, but we don't know how many people we're going to have in this example. So let's go ahead and create a vector, and we're going to use the vector macro here. Now you'll see here, I was having some issues with Rust Analyzer yesterday because of I was playing with it before the stream and ended up messing with the configuration. Got that fixed, thankfully. So today we've got that going, and you can tell that this is not code that I've written. Obviously, this is just my Rust Analyzer showing me the type that people is here, and it's a vector of, and it doesn't know what it's a vector of because we haven't given it enough information to really tell what it is a vector of. But we're going to provide various person structs inside of here. In order to make this easier, just as a recap of some of the things that we did yesterday, I'm going to create an impl here, and if you were around yesterday, you'll know that impls are for creating functions that are associated, functions and methods that are associated with different types. So we're going to create a new function here, which we learned yesterday is just a convention for functions that create a certain type. So there's nothing special about new, it's just a name that we've picked. And we'll say person here, and we'll pass in to our function here an age and a height. And so and we can do age, height. Now a neat thing that Rust stole from JavaScript is that when the field name and the variable name are the same, you can just go ahead and do it like this. So this is equivalent to what we had before as a shorthand. All right. So chat is asking if this is a beginner thing. This is definitely aimed at beginners of Rust. So if you're an advanced user, we may not cover some things that you've run into before, but we're aiming for people that have seen Rust before, let's say yesterday, and so have a basic-ish familiarity with the syntax and stuff like that. But don't worry, you can ask questions if you don't have it, and then really with a focus on bar checker. If you have no experience whatsoever with Rust, this might be a little fast at the beginning, but that's why we're doing this recap here. So don't hesitate to ask questions when you see something that you don't understand. But today we're really going to focus on specifically on the borrow checker. All right. And we haven't even really talked about what the borrow checker is, but we'll get to that in just a second. We're just kind of writing some code here. This is a little bit of a recap from yesterday. So I'm just going to call this new function here with, I don't know, how old is this person? I'm 31 years old and I am 197 centimeters tall. And let's say the second person here is going to be 58 and going to be 160 centimeters tall. That sounds about right. All right. So we have our vector here, and you can tell that Rust Analyzer now knows what's going on. With our people vector here. It knows that it's a vector of persons. And let's imagine that we want to this example is going to be very simple, but imagine we have a function that we need to write called first. And it is going to take in this collection of persons, this people collection. So we'll call this people. And it's going to take in a vector of persons. And it's going to return the first person in that collection. So this is, this should be pretty familiar to if you've done some programming before. You can imagine that you would write something like this, right? There we go. Now, the code is not going to compile, and that's exactly why I've written it this way. We're going to talk about why it's not compiling. All right. So presumably we can say the first person is by calling this first function here, passing in the people vector, and that will give us the first person. And then, we got the first person, so we can go ahead and say the person is blank years old and blank centimeters tall. And we just got to say first dot age here and first dot height. All right, I'm going to widen this out just a little bit here and maybe go down one. So let me know if this is too small for you and I can bump it back up. All right, so any questions here? It seems we have a question about why there's no return, explicit return. So it is totally legal and valid Rust to do this as well. Of course, it's still not compiling, but the return is totally fine to do here. Rust is an expression-based language, and what that means is that the last element of your functions are implicitly returned here. So whatever's last in your function will be returned. If you're familiar with languages like Ruby or something like that, then you'll be very familiar with this concept. A lot of functional programming languages work this way. You don't have to. You can do early returns. If you want to do some early returning, some guard statements and return early, that's totally cool and stuff, but you don't need return if the last thing, to return the last thing here. All right. Okay. So we've written some code. Let me know if there's anything about this code that you want to talk about, but this is kind of the example that we're going to start with, and we're going to really explore the borrow checker and why this code here doesn't compile deeply. So first of all, what is the borrow checker? Well, Rust is a systems programming language, and it does not have a garbage collector. What that means is that the memory inside of your program is not managed by a garbage collector, as you would expect in Java, C#, JavaScript, Swift, whatever. And yes, Swift has garbage collection. It's a different type of garbage collection than other languages. It's not a tracing garbage collector, but it's still a form of garbage collection. Rust does not have that. Rust has the same form of the same form of memory management that C and C++ have, in that it is up to the programmer to manage memory. But with the caveat and the difference to C and C++, that the memory management that you provide as the programmer, if you use Rust in the safe variant, so there is a way to turn this off, but if you use safe Rust, you cannot get it wrong. You might be able to leak some memory. So that's you're not protected against that, but you will never have any of the typical memory management issues that you would have in C and C++. If you've done any C and C++ before where you have something like use after free, where you free some memory and then you accidentally use a pointer to that memory afterwards, that's impossible to do in Rust. Double free, all these typical things, and we'll talk a lot about these as we go along. So you got to get your mind set to think about these things in terms of memory management and in terms of when memory will be freed. And that's exactly what we're going to be talking about today. We can no longer rely on a garbage collector to just free that memory whenever we're not using it anymore. We don't care when it happens, but just at some time when I'm not using it, you can go ahead and free it. We don't have that luxury in Rust. We know we will have to be keenly aware exactly when everything is cleaned up for us. All right. So there was a question in chat about some syntax here. This vec exclamation point. A vector is a growable collection. In a lot of languages, you just call that an array. Arrays in Rust are fixed size. Vectors are growable collections. Otherwise, they're basically the same thing. And this vect exclamation point is simply just a macro. That's what the exclamation point signifies. Printline and vec are macros that creates a vector and pushes these two elements onto it. We can write this without using a vector, but we would have to create the vector first and then individually push each item onto the vector. This vec does that all for us. So this is a convenient shorthand for doing that. All right. And then there was a question, why are both the var and function called first? I don't know, because I'm bad at naming things, I guess. What would you like to call it? F or person? Let's call it person. Hopefully that's a better way so that we don't get confused here. All right. So now that we're in the frame of mind of thinking about memory management and things like that, we should ask ourselves, okay, when we allocate memory, when will that memory be freed? And if you know anything about the heap versus the stack, you'll know that when we create a collection of something, we're going to have to put it on the heap, because this is dynamic memory. We put it on the heap, and at some point in our program, we will have to free that memory. And in C and C++, you would typically allocate memory with a function called malloc, and then free that memory with a function called free. In Rust, you don't typically do those things manually. Vec here will allocate space on the heap for two person structs to live in. And then when will that memory be freed? And this is the core concept of Rust. It comes from the idea of ownership. Now, what does ownership mean? It means that every value in Rust has an owner, a variable name, or better said, a binding, like people here. This people variable name, this people binding, owns this vector. So when we say it owns, what we mean by that is it's in charge of its memory. And when a binding goes out of scope, which we know about scope in any language, right? This is a scope here, right? And when people goes out of scope here, the thing that it owns will be freed. So when we look at this code, for instance, we can see, okay, people here gets created and people goes out of scope at the end here. And that's when the memory will be freed. Now, if you've done some Rust programming, you know that's not completely true the way that we've written the code. After all, it doesn't compile. But that is 100% true if we go ahead and say this right here. So people gets allocated onto the heap, and when people goes out of the scope, because it owns the memory inside of vector, and somebody's asking for bigger font, yes. Hopefully this is that viewable? When people goes out of scope, then the memory will be freed. So you have to remember that. In Rust, you always should have in your head, okay, a piece of memory, like this vector, what owns that memory? If you can answer that question, then you can answer the question of when does that memory get freed? All right. Okay, so if we write a function like this, there's another concept in Rust called moving. And what moving does is transfer ownership from one binding name to another. All right? So when we pass people into our first function here, what happens is we move the ownership from this people binding into the people binding right here. And of course, we all know this can be, let's call this PS for persons. So now they're not named the same thing. So ownership of people is being transferred from here, from this people binding. Sorry, the ownership of this vector is being transferred from this people binding to this PS binding. So we've moved ownership. So now, since we've moved ownership and this PS owns the vector, we know where this vector will be freed. It's whenever PS goes out of scope. And so this vector will no longer be dropped at the end of the function. It will be dropped, or it will be freed at the end of this first function. All right? So we have this idea of ownership. A piece of memory belongs to a binding, and whenever that binding goes out of scope, we free the memory. But we can transfer ownership when we move variables. And there are various times when moves happen. One of them that we're seeing right here is we are moving the vector into a function. So when you call a function, whatever, your arguments get moved into that function. That's just how functions work in Rust. Any questions about this? All right. All right, good. It seems like some things are clicking before. That's good. All right, so we've moved the people vector into the first function. This vector now is owned by PS, and we know that we're going to drop PS at the end of first. That's great. Okay. Now let's take a look. Let's dare to take a look at what actually the error message that we're getting. It says cannot move out of index of vec of person. Move occurs because it has type person, which does not implement copy trait. Okay, so what the heck does this mean? So we learn that calling functions, the arguments get moved into the function. Another thing that moves values is by indexing into a collection here. So we are trying to move the ownership of the first person, the person at index 0, out of the vector and return it from our function. And you might be wondering, okay, shouldn't that work? But let's think about this. Okay, if we move the first person out of the vector itself is going to be freed or just destroyed at the end of first, but we're trying to return the person here from the function. We can't do that. Why? Because PS, the vector, and of course the vector, when it's destroyed, all of its elements also get destroyed. PS will be destroyed at the end of the first function here, at this line. But we've moved the person out of here. So we would end up moving it somewhere else, and then later on, person here is person owns this person struct, and it will be destroyed here. We would end up destroying this person struct twice. We would call the destructor twice on this person struct. We would be freeing it twice. This is a double free. In a language like C, this is totally valid to do, and in this case, it probably would work. Rust right here is being quite pedantic. This case, they're most likely things would work, but actually you don't know. We're not freeing anything, we're not using anything in the heap anymore, but if we were to write more code that actually allocated more things in the heap, this memory that person is involved, that person uses, might be overwritten with something else. All right? So how do we get to this to work? We want to, there's multiple ways, right? But the first thing that we should think about is there a reason that we're moving first the person vector into first. Why are we moving it into? Well, so far we're moving it in there because we don't know any other way, right? We don't know anything other than to move into a function. But this is where borrowing in Rust comes in. So instead of moving the thing into the function, you just let the function borrow it and say, hey, like, I still am the owner here. I own this thing. I will destroy it, but like, you can have it for a little while. And what Rust does is ensure that the time that this function is borrowing the vector here is not longer than when we will eventually destroy the thing. So how do you borrow a value in Rust? Well, it's quite simple. You just add an ampersand before it. So now, and we're getting an error here because it's saying, hey, you are passing ownership of this vector, but you said you would give me a borrow of the vector. Okay, that's fine. I'll give you a borrow instead. Okay, so now first is borrowing vector, and that means that we don't move people into the first function. So PS won't be destroyed here because PS doesn't have ownership over that vector. It just is a borrow. And so where will the vector be destroyed? It will be just like way back when we first started writing this code. It will be destroyed at the end of main. All right. So you can think of this just like kind of books is a good analogy here. I own a book, and I can either transfer ownership to you and actually hand you the book and say, you are in charge of it now. You can do whatever you want. You're in charge of making sure it gets recycled properly when you're done with it. Or I can say, hey, you can borrow this for a little while, but I'm going to need it back. And that's exactly what we've done here. Instead of transferring ownership to the first function, we just say, hey, you can borrow it. And someone in Delphi Mielmo is saying in chat that this is kind of pass by reference instead of pass by value. Yeah. There are subtleties here that we're getting into that are different than in some other languages when it comes to that, but roughly what you can think of here is pass by reference instead of pass by value, if that's a comfortable thing for you. At the end of the day, what is this? In machine code, this is probably just going to be a pointer of some sort, but we're at a higher level now. We're not trying to think about pointers and stuff like that. We're just thinking about borrows and ownership. And Russell Westbrook is asking, is ampersand a pointer to a static variable? I wouldn't say it's a static variable. I mean, if you want to think of it that way, you can. Static variables in Rust have a very specific meaning. I'm just going to say that at the end of the day, you can think of a reference. This is called a reference, so you should use that nomenclature. But at the end of the day, yes, it's probably going to be a pointer. All right. So the code is still not compiling because we're still trying to take ownership of this person. Wouldn't it be great if instead of trying to take ownership of the first person, we just say, hey, you've let me borrow this people collection. I'll send you back a reference to the first person. So that's exactly what we can do. We can say now that instead of trying to move the first person out of the PS vector, we're going to return a reference to that first person. And it's still not compiling because it's saying, hey, like you're trying to return a person, like an owned person, the like ownership of this person, but instead you should be taking a reference. And so that's really easy to add with another ampersand. So now the code finally compiles. We have some warnings here. That's what the yellow means. Just some like hints because we're not using person, for instance. But effectively what we've done is we've said, first is no longer taking ownership. It's no longer going to destroy that vector. It's simply borrowing it, and we're going to return back a reference to the first person in here. And now person up here has ampersand as ampersand person. It is a borrowed person instead. And we can still use it just fine in our print line here. All right. If we run it, we can see the person is 31 years old and 197 centimeters tall. All right. This right here is basically half of what you need to know about the borrow checker in Rust. So this is really important to know this, the difference between moving values, transferring their ownership, basically saying to another variable, you're in charge now of freeing this thing. And then we have borrowing, which essentially says, you can have this for a little while, but I'm going to need it back. All right? And Chad is asking, is this the same thing as string, capital S string versus ampersand stir? Yeah, it's very related in the fact that ampersand string is an owned string. That means when the variable that's tied to it goes out of scope, that string will be freed, and all the string data will be freed, freed from the heap. And ampersand stir that we saw yesterday is simply borrowing and looking. It's like a string view. So there's a little bit of difference with ampersand stir that we probably won't get into today, but you can effectively think of it that way. There's also ampersand capital S string as well, which is truly just a borrowed string. Maybe we'll talk about that at the end, what the differences are there. Any more questions about this? All right. So, let's go ahead and say that we want to create a function called print. And what print is going to do is take a person by value. So it takes ownership of person, and it's simply going to print this out. All right. Now we know, where will this person be destroyed? It will be destroyed when it goes out of scope, because we have ownership of person. This person variable is in charge of the person struct. It owns it. And when it goes out of scope, it will destroy it. There's a question, is it possible to lose the reference during borrowing? No, it's not possible to just lose it. Rust ensures one way that Rust references are different than pointers, for instance, is that references are always valid. They always point to valid memory. And Rust statically confirms that this is a case. If you find that to not be a case, then you have found a bug in the Rust programming language. And they're never null. So we know when we pass in an ampersand vec here that we have a valid reference, a valid pointer to a vector of persons. All right. And we know that, for instance, we can't, if we try to call print, this print function with our person here, it won't compile because it expected an owned person and we gave it a reference to a person. Now there are ways to turn a reference into an owned value, but we're not quite there yet. We'll look at that in just a second. All right. But if we go ahead and just change this now to ampersand person to borrow it, then it's fine. And of course, if we want to print multiple times, that's also fine. But imagine, let's say, we had an owned person 2 here. We're going to say person new. The person's going to be 17 and 183 centimeters tall. All right. Oops. I didn't mean this here. There we go. So we have person 2 here. And we're going to change print back to taking it the owned version, right? And if we pass in person2, this is fine, right? Person2 owns this person struct, so we can pass ownership into the print function here. This is totally cool. What happens if we try and do it again? We can't do it. Why? Because we've passed ownership into the first print, the first call to print here. We can't pass ownership again. Because we know when we pass person2 into print, print will drop, will destroy, will free that person. So if we were able to do this, where we call print twice with the same person, it would be freed twice. And that is a double free. So we are preventing here double free. All right. There's a question about, have you considered rewriting Visual Studio in Rust? I have considered it, yes, but I am in no way connected to the Visual Studio team, so it doesn't matter what I consider. And I'm pretty sure the Visual Studio team has not considered rewriting Visual Studio in Rust. The reason is Visual Studio is very old, has a lot of code in it, and rewriting it in Rust would take years and years and years and years and years. Rewriting it in any language would take years and years and years and years. And, you know, it's up to the Visual Studio team to decide if that's worth it or not. And I think they probably have determined that it's not worth it, which doesn't seem like a terrible decision. All right. So any questions about ownership here? We've passed ownership into print. Ownership of person2 into print, and then we try to pass ownership again, but we can't. And if we look at the, and I'm just going to pop this open and do a cargo check real quick to see the nice clear, cargo check. And this is what Rust is telling us. Use of moved value person2. Move occurs because person2 has type person, and we haven't talked about the copy trait in just a second. We'll talk about that. We've moved into print on line 9, and then we're trying to use it after we've moved it. So we can't do that. Not only can we not move it into things, but we can't, you know, let's say we just wanted to like get the age of person2 here. We can't even do that, right? Because person2 has been moved into print. There's a question, I'm not sure about PS declaration. It is declared and initialized same time in FN first. Nature Hermit, can you perhaps ask the question in a different way? I'm not exactly sure what you need. PS here, of course, is an argument to our function. So whatever we pass into first here, that's what we will bind to the name PS. So for instance, up here, this people, this reference to people will be referred to by PS. It's a function argument just like in any other language. So there's a question, what's the reasoning behind this implicit mutation? Can you clarify what you mean by implicit mutation? Because we're not actually mutating anything here. We are destroying it. Of course, this is all compile time, right? So we're not actually changing the value. We're just saying, Rust is just saying, hey, you can't do that because you've passed person2 into print. So there's no mutation going on. We're going to look at mutation in just a second. If you can clarify what you mean, I'd be happy to answer the question. All right. Let's take a look at mutation. What happens if we want to write a function that simply changes the age by year? Let's call it birthday. Now, of course, we can take in a person here, and person age equals person dot age plus 1. This works totally fine. Doesn't work totally fine because in Rust everything is immutable by default. So actually we have to say, hey, we're changing the person variable here, so we have to declare it mutable. All right. This works fine. But it's maybe not the most useful function in the world, because where will person be destroyed? At the end of this function. So we'll call birthday. The age will increase, and then we'll free its memory. Maybe not the most useful. Can we instead borrow it? Like this. And we cannot. Cannot assign to person.age, which is behind an ampersand reference. And let's see if we actually, if we go ahead and, yes, even Rust is telling us what it thinks we should do. So help, consider changing this to be a mutable reference. So there are two types of references in Rust. There are immutable references, which we've already seen, this ampersand person, and there are mutable references, which we have not seen, which are ampersand mut, just like this. And we can only mutate through a mutable reference. We cannot mutate through an immutable reference. And now birthday works just like before. We can say, birthday, and we can pass in a mutable reference to person2 here. And we have to say, hey, we're going to be mutating person2. Again, Rust is immutable by default. So now this all works fine. It's compiling fine. This totally works fine. Does this make sense to everybody? There's some talk in chat about move semantics versus copy semantics. We're going to get to that in just a second. So hold on. Yeah, so there was a question of before, when we were calling print twice with person2, like we passed person2 into this print function and then we could no longer use it. That's kind of the point. Like we have declared that the function print here should be responsible for freeing the thing. Of course, we can change print to not do that. Now we have said that print shouldn't destroy person, it should merely borrow it. So we have control over when person will be borrowed or not. All right? And again, we don't have a garbage collector here, right? We don't have a garbage collector that can make these decisions for us. We have to decide when our memory will be freed. And we are telling Rust, and print should free person here when we declare it like this. And when we declare it like this, we say, hey, print should only borrow it. It should not take ownership and therefore free that person, destroy that person. All right. Okay, so we saw above that we were able to pass as many mutable references as we want. Can we pass as many immutable references as we wanted to when we called, let's see here. We can call first, for instance, many times. So because we're passing in an immutable reference to people, this is totally fine. We're passing people over and over and over again. We get a lot of mutable references back here. It's just complaining that we're not using person anymore. That's fine. Can we do the same with birthday here? What if we try and mutate it twice? Okay, we can. That's great. But what happens if we move this out and say we have a mutable person here? Now, mutable person is a variable that is a ampersand mute. And we can pass it into birthday and pass it into birthday. And this also works fine. It's totally fine to do. All right. So it's totally cool to discretely pass in mutable references to things and multiple different functions. That's fine to do. All right. Any questions about this? So PS on line 3 is a reference to people, but PS declared in first is a copy. So it's not a copy. PS here is not a copy at all. It is a reference to the previous vector. It is literally, it's pointing to it. If you've done any pointers before, it really is just saying, hey, the vector of people somewhere else. So it's not taking a copy, it's not copying it at all. And Crateless is asking you, cannot use person2 after this call to print. That is correct. If we try and do that, it will fail to compile. All right. Is it necessary to make a call that destroys an object by the end of main? No, it is not necessary to do that because, again, when bindings that own a particular piece of memory go out of scope, they will be destroyed. So people owns this vector here, and when it goes out of scope, down here at line 15, it will be destroyed. There's a question, why can't you use ampersand mut p2 after line 22? Can you clarify that, Excellent Dragon? I think you should be able to. That works fine. All right. We are reaching the end here, so we need to talk about one last thing. The one last thing that we need to talk about is the differences between immutable references and mutable references. Now, so far what we've seen is they seem to be the same, except that when you declare a mutable reference, you're allowed to mutate, and when you declare an immutable reference, you're not allowed to mutate. But there's actually an important distinction between that. What the important distinction is that mutable references, you're only allowed to have one of them at a time. All right. So here, our mutable person on line 11 is a mutable reference to person 2 here. But if we try to take another mutable reference to person 2, and Rust is being very clever here because we're not actually using it, we have to use it, it no longer compiles. And let's take a look at the error message that we get. So, cannot borrow person 2 as mutable more than once at a time. We see the first mutable borrow occurs here, and the second mutable borrow occurs here. And why is this? This is a fundamental rule of Rust. In Rust, you can have either as many immutable references as you want at a time, or, and this is exclusive or, so it's one or the other, or one mutable reference. All right? And we are violating that rule here by having two mutable references. We're only allowed to have one mutable reference at a time. So we're not allowed to do that. And we said we're either only allowed to have one mutable reference or as many immutable references. What happens if we try to take an immutable reference here? Again, and this is maybe a bad name now because it's no longer mutable. Person 2. Getting a bad error message there. It's not really bad, but this gives us a, let's see. Okay, so real quick, unfortunately we don't have a function that just takes a immutable reference. Let's say age is going to, let's do print age is just going to take a immutable reference to the person, all right? And we will just say the person is blank years old, all right? So again, this is taking an immutable reference, person.age. This is taking an immutable reference, and so person will not be destroyed here. We're simply borrowing it. So up here, we can go ahead and call print age with our, let's call this immutable person 2. And now we see the error. We cannot borrow person 2 as immutable because it's also borrowed as mutable. So this is exactly what we have to deal with. We are only ever allowed to have one mutable reference to a thing or as many immutable references as we ever want to. All right. Someone's asking in chat about RC and ARC. Unfortunately, I don't think we're going to have enough time to tackle RC and ARC today. But I'll put this on a little bit later. I have my own stream where I stream about Rust, and I'm more than happy to have future streams where we kind of continue this conversation and talk about those topics that are the next step in Rust Borrow Checker. Go ahead and throw up my information here. This is my Twitter handle up top, @Ryan_Levick. You can follow me on Twitter, and I tweet about when I'm going to go live on Twitch, and this is my Twitch where you can follow me as well. So if you're interested in learning more about Rust, then definitely give that a follow. Just leave that up for just one more second. All right. I want to talk about one more thing before we slowly bring this to a close. And that is this copy trait that keeps popping up. So let's go ahead and get rid of this code real quick. Gonna get rid of all this code. Blah, 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 blah. And for instance, when we tried to call print multiple times here, where we get this answer. Let's see. I need person 2 again. So if we create person 2 and we try to call print multiple times, the code does not compile, and it keeps making reference to this copy trait. So move occurs because person 2 has type person. Everything that we've been describing so far about moving values from one variable to another are summed up with this idea called move semantics. So Rust has this idea of move semantics, and all that means is exactly what we've been talking about so far. When we pass variables into functions, they get moved into functions. Rust moves things by default. Now, if you're coming from a C++ background, you know that C++ does not have move semantics by default. You have to explicitly move things. C++ has copy semantics. So instead of moving things into functions, you copy them into functions. But what happens if we want that behavior? Let's say we don't want to have to deal with moving things all the time. In fact, our person struct down here is just 2 numbers. Like, it's totally fine to just keep copying it all over the place. That's totally cool. It's only 2 numbers. Copying is really not that expensive. How would we go ahead and opt into this copy semantics so that when we pass a person into a function, instead of moving it in, it simply copies the thing? We do that by using this funny little syntax called derive, and we derive a trait, and trait is just simply like a marker of functionality that a type has. You can think of them like interfaces in other languages. We have to derive copy here. Now, copy will then tell you I can't be copy unless I'm clone. So we have to also derive clone. And what clone is just like copy, except that it's explicit. So if you want to be able to copy values by calling a function to actually copy them, you have to implement the clone trait here. And copy simply says make that implicit. So now our code up here compiles. Because person2 is no longer moved into the print function, it has copy semantics, it's now copied into the print function. And we can see that if we go ahead down here and say, print now, let's have a birthday before we print. So before we print here, and we have to declare this as mutable, before we print here, the person will have a birthday. All right. And if we go ahead and run this, cargo run, you can see that this person2 is 32 years old, 100 centimeters. Even though we had a birthday twice for each time that we called the print function, because we copied the person into that print function, they will end up having the same age over again because they were copied in. An excellent dragon was, what if you only want this behavior in one specific function? Unfortunately, you can have that. You can, as long as that type implements clone, you can specifically call clone on that. So let's say we remove copy here. Our person, this will no longer compile up here because person2 no longer is copy. It no longer has copy semantics. It now moves into print just as before. But person implements the clone trait. So if we want, we can call clone on it. And this will literally clone the value. And why is it complaining now? Oh, because it's been moved in. We have to do it the other way around. We clone here. We get a copy of person2 and move that into print, but person2 has not moved. And so now we're allowed to move person2 into print. But of course, if we call it a third time, it will complain. So if we want to be able to do this, we'll have to clone this one as well. So this is how you get it sort of on a per function basis. So there's a question, is it quite tricky to refactor Rust code? Actually, no. Rust code tends to be extremely easy to refactor, surprisingly. The reason is because the compiler is quite picky. And so as long as you get it to compile, which, at first, if you're not used to Rust or something like that, it might be tricky to refactor because you're constantly having to think through these things. But, when you get used to Rust, this all becomes second nature. You just start thinking in terms of borrows and moves and things like that. And then you can simply refactor knowing if you forgot something, if you, forgot to touch a file over here or change this function over there or something like that, you don't have to worry about it because the Rust compiler will tell you, hey, you forgot it over here. You're doing this thing even though you changed the code over here to change from copy to move, and it will complain at you. So in fact, like there are many stories of people taking code bases written in Rust that are hundreds of thousands of lines long, doing massive refactors on them, and then once they get the code to compile again, it ends up working like it did before, because the compiler is very good at what we're doing here is essentially proving to the compiler that we are creating a correct program, and the compiler, once it's satisfied, says, okay, you're allowed to run this program now. Other languages like C and C++ take a very different approach to this, where it's quite easy to get something to compile, but will it work correctly is a whole nother story. And Rust tries to front load the cognitive load of getting something correct to the compile stage instead of at the run stage. There's a question: is it possible to write C++ in a Rusty way? Yes, absolutely. And I think if you if you write C++ for work, or if C++ is your main language, I still would highly recommend learning Rust, because you can take a bunch of the learnings that you have from Rust and then apply them to your C++ code. And if you do that, your C++ code should become much easier to maintain. You won't have the same level of, the C++ compiler will still not prevent you from doing something wrong, but you can apply patterns that you have to do in Rust to C++. And even though you're not forced to do it that way, they're still good patterns. And Orkblood is asking, don't know either C++ or Rust, which one should you learn? My answer to that is always both. But if you have to choose one, C++ is definitely a much more established language. So if you're just like wanting to get a job, let's say in the gaming industry or something like that, you'll probably have a lot more luck with C++. There's simply just it's an older language. It's been around a lot longer. It's more established. So there's going to be more opportunities in C++. I personally find Rust a lot easier to learn. I spent a long time trying to learn C++ and would always, it can be a very frustrating language at times. This is my personal experience, but for me personally, it was a very frustrating language to learn. It's a very, very complicated language. There's a lot of features in it. Rust is tough at the beginning, but once your code compiles that you really have done something right. That you don't have to sit there in a debugger debugging why your code is segfaulting and stuff like that, because there are no segfaults in Rust. In safe Rust, you cannot have a segfault. If you get a segfault, there's a bug in somebody else's code, which is good to know. All right. So we're gonna end around here. Feel free to throw up any last questions. If I missed a question, please ask it again. And I'm gonna end with a couple of words here. We've taken a look here at the Rust borrow checker. We've learned a couple of things: that a piece of memory is owned by a specific binding, and when that binding goes out of scope, that memory is freed. We can move ownership between variables. For instance, when we take an element out of a vector, when we pass something into a function, we move the ownership from one binding to another, and then that new binding will be responsible. If we don't want to move, we can borrow, and we can borrow immutably or mutably, but we can have as many immutable borrows as we want, or one mutable borrow. And this is very important. We can have either or, but not both at the same time. And if we don't like this whole move semantics that we have, for types where it makes sense, where all of its fields implement copy, then we can go ahead and implement copy as well. And now our type has copy semantics instead of move semantics. All right. Now, this has been a whirlwind tour. If you feel like you are in a stable position right now with a Rust borrow checker, then you are light years ahead of a lot of other people. This takes a while to kind of settle in your brain. If you're not fully comfortable with everything that we've talked about today, don't worry. This will be posted on YouTube. It will be on Twitch. go ahead and watch it again. Take a look at the Rust book, which is if you'll find it on rustlang.org. This is a great resource for this. Rust by Example is really great. There's Rustlings. There's a whole bunch of different resources for kind of working through it. And realize that this is the core of Rust. So if you're struggling with getting code to compile here, don't worry. It's not you. This is the tough concept about Rust, but it's very, very worth it. Once you learn this, then you can feel comfortable about the code you write and never, ever experience a seg fault in a systems programming language. That's a huge deal. I almost never use a debugger when I use Rust. So because, what's there to debug? All right, real quick, a couple of last questions just to end on. So can you edit a fun definition to pass by copy? So it's not the function definition that determines whether a value is passed by copy with copy semantics or move semantics. It is the type itself. So right now, our person type is declared to be copy, so it will be copied when passed into a function. But as soon as we remove this, it will now be moved in. So no longer copied, but moved into a function. So, and there's a question of how far do you intend to go with this series? Unfortunately, this is the last that I will be on this channel. So we're just having a Rust week here on Microsoft Developer Twitch. But over on my other channel, I basically only stream about Rust, or recently did a series on ELF executables in Linux. So I do some computer science, some Linux stuff, and things like that. But if you're interested in that, let me know. It's easiest thing to do is follow me on Twitter and just ping me. Hey, it would be great to see more about this. I would be happy to do a continuation of this series over on my channel. So please do let me know. And about joining Eric St. Martin's stream, he's my colleague. So Eric and I have talked about me jumping on his stream. We're in different time zones, so it's not always easy to do, but I would absolutely love to be on Eric's stream. And one last thing to throw up, here's my social information here. At Ryan_Levick is my Twitter handle, and below that is my Twitch channel. So make sure to follow me there if you're interested in this. And I believe that was all the questions that we had. So thank you very much. I'll be sticking around a little bit in chat after this ends, and of course I'm on Twitter. Feel free to hit me up there. And I hope everybody had a good time with the stream today and has a good rest of their day. All right. Bye-bye.